The course website is given right here. So you can just click on that. This is what it looks like. This ever loads for me. So the course website has basically all the things you need to get through this class. So the slides, for example, are up. I'll make sure that they're up every time before class. You can look through the slides along with the lecture. And there'll be other things here as well. Basically, everything I list that's required of you for this course, I'll tell you about just now, you're going to find it on the website. So we're going to use Piazza for announcements and discussions. Again, the Piazza link is at the top of the course website. Make sure you sign up for our Piazza group, because I'm not going to use Canvas for anything else than basically just submissions, homework submissions. So all the announcements for the class are going to be run through Piazza. And yeah, Canvas just for basically collecting submissions and as a grade book where you can see all your grades. There are no formal prerequisites for this class. I don't think we have any formally listed. The class is going to be fairly fast-paced. What we're going to assume that you're kind of familiar with are the following. So real analysis, calculus, and linear algebra. A ton of basic convex analysis is rooted in these topics. So if you're rusty with things like taking gradients and Hessians and the chain rule and all that stuff, it's a good thing to refresh yourself on right now as we start. You're going to need to have some programming experience, because every homework's going to have a programming problem. I skipped the second one. I'll just continue on with this one. So we don't really force you to use any particular language. You can use essentially any language you want, but the ones that we'll be able to provide support with are R, Python, and MATLAB. Our TAs are familiar with a mixture of those, so you'll probably have one person who can help you if you're stuck on a programming problem in one of these languages. If you want to go off and use Julia, more power to you. If you want to use Lisp or something, then I don't know we can help you with the homework. So it's up to you, but I think if you stick to one of these three, then you'll get the most help. I skipped over this one. So one thing that we're going to assume that you are familiar with is what are the core problems that we are interested in machine learning and statistics. So as an example, things like support vector machines, things like the lasso, etc. These are things that have a very interesting optimization component to them that we'll talk about in detail throughout the course. But we're not going to provide a ton of motivation for why you should care about support vector machines or why you should care about the lasso. We're going to kind of assume that you are already familiar with that from a previous course. If you don't know something about these estimators or these problems, I think you could still take the course and you could still do well. I think a lot of it would kind of not be very well motivated in some sense. So, this is a soft prerequisite. The last two items here, I don't know, these are really vague, but we're going to be assuming that you're kind of familiar with, like rough working knowledge of data structures and computational complexity. So if we say something requires, linear time or quadratic time, this kind of thing, we're kind of assuming you know what that means. And this one is the most vague of all. A lot of what we do, we're going to kind of be rigorous about why algorithms converge or why certain things occur in terms of convex optimization. So you have to be comfortable with some kind of level of formal mathematical thinking. We might hit on topics outside of these things like analysis, calculus, linear algebra, and we're just going to assume you're comfortable with kind of rigorous mathematical thinking. So I think you could take the course and you could do well if you didn't have all of these things, but it would require you to kind of be active in catching up. So come talk to one of us if you're finding that you're falling behind. What are you required to do? Here are the things you're supposed to be doing this semester. So you have 5 homeworks paced out there's about 1 homework every 2 weeks, and then they get spaced out a bit more towards the end of the class. The homeworks typically have 3 written kind of more mathematical type questions and 1 programming question. You have 2 little tests. So I started doing this a little while ago, and I think it's been a low stress way to just evaluate whether people know some of the basic things we covered in the course, and I've come to really like it. So in place of a midterm and a final exam, you just have what I'm calling a little test It's 30 questions, true or false, multiple choice. And it's supposed to be the kind of thing that you don't really need to study too hard for. If you've been keeping up with the lectures and you want to look over your lecture notes before the test, you should do fine. They're not supposed to be trick questions. They're just supposed to be kind of the bread and butter that we learned. One project, I'll say something about that in a second. And many easy quizzes. So the quizzes are like the little test, not things you should have to study for. I mean, even more so for the quizzes. So at midnight, the day of every lecture, you have a quiz due. And it's linked on the course website. So I'll just show you that here. It's linked right here, quiz. And you have to sign up for an account through the system that SCS created called Q&A. Stands for question and answer. And it's an online system for taking quizzes. You can sign up with your Andrew ID or your Andrew email account. And the questions are all true, false, multiple choice. And maybe if we have time at the end of the lecture, I'll just even do some of the questions with you. They're supposed to be very easy, and you can try questions many times. If you get them wrong, on the first time you can try them again a second time, and a third time, and so forth, and you get half credit for a right attempt if you didn't get it right the first time. So the very worst you can do is 4 out of 8 if you just brute force the quiz. But if you try not to brute force the quiz and you kind of remember some things from lecture, you can do better. So again, these are supposed to be just like a low-stress way of kind of reaffirming the basic concepts in lecture. All right, the project. So the project is, in a nutshell, trying to get you to do something useful / interesting with optimization. We ask you to do it in groups of 2 or 3. You can do the project alone, but I think that that's an exception that we would grant if there was a real reason you didn't want to work in a group. We definitely prefer you to work in groups of 2 or 3. If you want to work by yourself for some reason, just come talk to one of us. We can grant an exception for that. There's milestones that you'll complete throughout the semester. There's milestone 1 due, I think, around the start of October. Milestone 2 due around the start of November. And then the final project is due at the end of the semester. I'm going to maybe just punt on giving you details on this. I'm still trying to figure out what I want to do with the projects. I'm thinking about making it more flexible than previous years. So I'll just say details to come. The first milestone is coming up at the start of October, but you don't have to have done anything kind of really by then. You have to just have decided on a topic. So don't stress out about it at this point. If you want to get started early on the project, just try to find some friends that have common interests to you and see if there's some topics that are related to optimization that you'd like to learn more about. That's a good place to start. And then I'll give you more details as they solidify. I think this is the last slide for administrative stuff. So scribing. So scribing is not required. It's strongly encouraged. I guess the consensus has been that people find scribed lecture notes useful. Basically, there's a LaTeX template up on the course website, and you can have there's a sign-up sheet that we're going to release where you can sign up to be a scribe for a particular lecture, up to 3 people scribing one lecture, and you'll just basically summarize what you heard in lecture into one coherent document. Give the PDF to Henry, who's one of the TAs. Shi Yen is his name as well, and we'll post it on the website. And we're expecting them to be done about a week after lecture. So whoever scribes today's lecture, there'll be about we're looking for you to give us a PDF back about a week later. So we're not going to be requiring scribes. So you might ask, what's your incentive to do it? Well, one incentive is that if you all scribe and people find scribes generally useful, then it'll be a good way to review the course material for the little tests. Okay, so maybe it'll just help you out in that regard. Another incentive is that we're going to informally use this to bump up your grade in boundary cases. So if you're like right in the border of an A- B+ and you scribed, then I'll give you an A-. That's what we'll say with scribes. So there's no component of your grade that's dedicated to it, but it can help in boundary cases, and it seems to be a useful thing for students. Lecture videos, our friends at Panopto are recording these, and they'll be available on the course website. I'll just say that there's supposed to be a helpful supplement to lecture, not a replacement. I always find it much more fun when people are actually here asking questions. I think you'll learn more by being here. Of course, attendance isn't required, so you can choose to not come and watch the videos instead, but I just think that's probably not an optimal way to learn. So it's best to attend lectures. Auditors, in theory, auditors are welcome. I actually see some open seats, so if you want to come to class rather than just sitting in, please fill out a formal audit form. Formally, at this point, I think we have no room for auditors. We're at max capacity. There are a lot of people sitting on the stairs, even though they're open seats. So we're at 152 people sign up for the class, and I think the wait list is at least 100. I don't know. I mean, it seems, I think it's large as well. So I think there might be room for auditors eventually. We'll have to see what the final class size ends up stabilizing at. And the last thing, a heads up, the class is not going to be easy. I think this class, the homeworks, require work. The material is challenging. But hopefully, of course I'm biased, it should be well worth it. I think that optimization kind of is, it's ubiquitous in statistics and machine learning. So having a solid grounding in optimization is going to open up your eyes to see things differently and maybe understand things at a deeper level. So we made it in 15 minutes. We finished the administrative stuff in 15 minutes. Yes? I can't remember. So the question is the homework, has the grading breakdown been decided? Is it on the, there might be on the syllabus. I think it's on the syllabus if you look. So let's just check that. Yeah, I'm pretty confident it's on the syllabus. We'll just get some proof of that. Yeah, there it is. So that's the grading breakdown. And there's a bunch of other stuff on the syllabus. Look through it to make sure that you understand, for example, the collaboration policy is described here as well. Okay, any other questions about the administrative side of things before we jump into the lecture material? All right, are we still good with the mic? I just knocked it off. We're good. Okay. So let's start the fun stuff. Optimization problems. I think it's not really arguable at this point. It's just a fact. They underlie almost everything we do in machine learning and statistics, and in other fields as well. I don't think everybody here is, a graduate student in ML or in stats. So in many other courses that you've taken, for example, machine learning courses, if that's your background, you learn how to translate some kind of conceptual idea. Like, for example, I want to fit a line through these data points. That's maybe. It's not a mathematical idea yet, but I want to fit a line through these data points that is the best fitting line. You learn how to translate that idea into something kind of mathematically well defined in the form of an optimization problem. Okay, so that we translate into, for example, I want to find the coefficients that minimize the squared error. So I want to do least squares regression, right, between the responses and the features. So that's an example of translating some kind of conceptual idea into an optimization problem. That's not going to be something that we're focusing on much in this course. Again, I'm going to be assuming that kind of skill is something that you've spent time on in other courses, and that you understand why certain optimization problems are well motivated. But in this course, we're going to really dive into this right-hand side, and we're going to talk about how to solve these problems algorithmically, how to understand solutions to these problems, maybe mathematically, and we're also going to be providing motivation throughout as to why this is a good skill to have. So what are the implications of having these skills? So just to get us going, why don't people tell me some examples in your own field? It could be machine learning. It doesn't have to be machine learning, though. It can be whatever your own field is, of optimization problems that are common. What are some optimization problems? Yeah?
Network flow.
Network flow. Okay. That's a good one. What is your background? Computer science. Yeah, so we'll actually talk about, for example, things like max flow quite a bit when we learn linear programming, but that's a good one. Other examples? Okay, I'm not sure that that's formally defined, but other examples, yeah. Okay, can you maybe give me a bit more?
Like in the prerequisites, minimize the time it needs for a ball to roll off a certain curve.
Okay, so this is like, I'm going to draw a picture. But maybe there are certain physics optimization problems involving Lagrangians. Is this called a catenoid? Is that what this is called? Not sure. Yeah, catenary. Other examples?
Minimizing the cost of providing electric power to meet demand.
These are all great examples, but they're very general. I'm not sure I know how to... Okay, optimal power flow. So there's a specific formulation of that problem. Is that right? And what are your guys' backgrounds? Okay, cool. Other examples? Yeah. Yeah, that's a good one. So that's a statistics example. We have some likelihood. It's a function of some parameters. We want to maximize the likelihood to find the parameters. That already encompasses, as an example, things like, least squares regression. And logistic regression. Other examples? Yeah.
You have a robot moving in an environment, you might have a cost map you want to optimize for planning.
So could I call that motion planning? Is that fair? So my understanding is that a lot of these problems involving motion planning are non-convex, but we didn't specify whether they should be convex or not. But it sounds like a hard problem. Yeah. So do you mean in terms of like compressed sensing, or what kind of compression? Okay. So maybe we'll just write compressive sensing as an example. Right, so there are many, and I think we were kind of a bit shy on ML examples, but I think it's because we probably all know a lot of ML examples. So support vector machines are another good one. A lot of regularized likelihood problems. These things are quite important nowadays. Things like the lasso as an example. So there are many examples we could give. I like to do this at the start of the class just to give kind of some flavor that it's really not everything. So what are some examples of problems we try to solve? Maybe let's say in machine learning, because this is a machine learning listed course, that cannot be formulated as optimization problems, but there are things that are kind of popular. Yeah. It's a good example. So the bootstrap is a method. It's not optimal with respect to any kind of criterion, but it's very useful. I want to get a sense of, for example, how variable a particular estimator is. If I want to estimate the standard deviation of an estimator, which we call it standard error, I could use the bootstrap. And it's something that statisticians think of as maybe one of the first tools they have in their pocket for solving problems, but it's not optimal. It's not defined as the solution to an optimization problem. Maybe there's some asymptotic theory that supports it being useful or even optimal in some regard, but the bootstrap itself is just an algorithm. It's not kind of tied to an optimization problem. Other examples? No, this one is, this is debatable. I would actually put this right in the boundary. So, a neural net has a criterion. We do things to that criterion, right? We do basically gradient descent. But then we also do a bunch of other things, maybe like dropout or other kind of tricks that we apply. So those tricks aren't really formally associated, at least not, let's say, as we currently understand them, as solving a particular optimization problem. But neural nets themselves, if we just ran, let's say stochastic gradient descent, it's solving a particular criterion. So they're kind of in between. Other examples, yeah. Yeah, it's a good example. I mean, I guess it depends on what we're using MCMC for. But sometimes we could think about it as being associated to optimization, sometimes not. I'll throw out another example. How about things like random forests? So random forests are, I've heard them called, permanently second place. It's like they're the second best estimator in any problem. They're not the best, but they always do close to the best. So they're very popular. That's all I meant to say. But they're not motivated from the perspective of one optimization problem, right? They're basically a way to combine through resampling a bunch of trees. And each of those trees is, you could say, also not motivated by an optimization problem. It's just a greedy heuristic. Yeah? So it's a good question. So the question was, how about non-parametric estimators? So it depends on what the estimator is. So here's a non-parametric estimator, smoothing spline. That's actually a solution to a particular optimization problem. You can also say an RKHS estimator. That's the solution to an optimization problem, reproducing kernel Hilbert space. So these things are non-parametric. They come from optimization problems. But other non-parametric estimators aren't necessarily. So maybe the most basic example of something that is not defined with respect to one optimization problem as optimal with respect to one optimization problem is kernel smoothing, right? I just lay down a kernel and I average points nearby with respect to some kind of kernel weights. It's another example of these things just kind of make sense from first principles as algorithms. We don't define them as solutions to optimization problems. But anyways, this was just an exercise to get us thinking and to kind of emphasize that optimization plays a very large role in let's say, machine learning, but there are other things that we do that are really purely algorithmic or methods-driven that aren't optimization-based. So moving on, presumably there's a lot of other people that have figured out how to solve problems, that are cast generically as optimization problems. In fact, you'll see already on the first homework, you're going to use a software tool that provides what we call disciplined convex programming framework. So it gives us a way of expressing very generic convex problems so that it can solve them, perhaps not super efficiently, but still very broadly. It can solve, really a ton of convex problems. So there's a lot of research that went into that. We can thank, Stephen Boyd, for example, and a lot of his students and co-authors for that. So you could ask, why bother? We already have something like CVX at our disposal, and even if I didn't have CVX, I could probably look up good software for SVMs. So, why would I bother? Well, I'm going to give you 3 reasons. The first is that different algorithms can perform better or worse for different problems. And just knowing, for example, that there is a QP solver out there that you can call doesn't always mean that it's going to be useful for your problem. Even if that QP solver can be very, very efficient for particular types of QPs, if it uses interior point methods, it could actually perform horribly for other types of QPs. And you might actually, prefer to do something different like coordinate descent. So you have a coordinate descent library at your disposal. You have a kind of, let's say, interior point method-based QP solver at your disposal. You need to figure out which one to use. And what we're going to teach you in this course is that you can kind of, through working knowledge of algorithms, you can kind of come up with some ground rules for when different algorithms will perform better or worse, depending on the problem characteristics. That's a very useful skill to have, even if you're not implementing the algorithms yourself, even if you're just kind of looking for available software. Okay, moving on from that, studying optimization, taking an optimization view of a particular problem can actually often lead to kind of a deeper understanding of the statistical procedure underlying the problem. This is kind of specific to machine learning. So I'll give examples of that, but a ton of statistical theory that we celebrate for things like high-dimensional estimators, many other modern things, it's actually grounded in an optimization view of the estimators. So in particular, using optimality conditions that kind of characterize estimators, it actually kind of leads to a bunch of really interesting and important statistical theory for them. And the last thing is, if you have a really, let's say, solid understanding of optimization, what's hard and what's easy about it, they can actually help you create a new problem that is maybe more interesting or even more useful than the one you started off with. Okay, and this is happens all the time, that people try to do something, it's computationally very difficult, so then somebody with a kind of really strong background in optimization comes along and says, I'm going to change the estimator slightly, I'm going to change the problem slightly, this thing is now much more tractable, I can compute it efficiently, and I'll provide some kind of maybe bound between what you're trying to compute and what I'm computing for you. Okay, so there are many good examples of that. You know, I'm not only talking about convex relaxations. Of course, maybe that's like one kind of big instantiation of this, taking a non-convex problem and relaxing it into a convex one that's possible to solve. I also mean kind of more subtle decisions between things like, here's the penalty in this convex problem. It's kind of complicated. I'm going to actually simplify it to be something different that I know I have algorithms that can actually take advantage of the structure of that new choice of penalty. So just a kind of a broad editorial comment. Optimization moves really quickly as a field. It's kind of insane how different NIPS proceedings are year to year, as an example, in terms of their optimization focus. Many years ago, I was at a NIPS workshop, and it was everybody was talking about distributed optimization. That seemed to be like the big thing. And then some years after that, it was non-convex alternating optimization, and that was the big thing. And now it's moved to something else. So it just seems to be kind of always experiencing a ton of interesting progress. That can be intimidating to somebody who's just learning the field and thinking, how can I jump into this? But I think it's actually a positive, because what it signals to you is that there's a ton of open problems in optimization, especially in its intersection with machine learning and statistics. So there's just a lot of really interesting progress to be made in open problems. And let's say even if you care about non-convex optimization, if that's kind of the field you eventually want to work in, I would argue that actually you need to understand convex analysis in order to do anything interesting in non-convex optimization. So this course is the place to start, even if you wanted to end up focusing on non-convex problems. So let me give you some examples actually, I'm going to try to give you an example of this one, number 1, and an example of number 2. And number 3, I'll just leave it to you to kind of look around the literature, or if you're interested, you can come talk to me after class. So here's a problem that I'm personally interested in. I've spent some time thinking about problems of this nature. The projector is kind of bugging out on us. 1 second. Okay, it seems to have fixed it. So in this problem, suppose we have an image, let's say, like, for example, this image, and we're going to encode, let's say, every pixel as a real value. So typically, we actually have 3 channels, red, green, and blue. So we'll actually have kind of 3 real values per pixel, but you can just think for simplicity, I have some kind of color scale. I'm going to convert, numeric values to colors, or I can make it grayscale. So at every pixel in the image, I have a real value. I'm going to call that y. And now I'm going to unravel that image into a vector. So y is just one big, long vector. If this is like, let's say, 300 by 100, y is of length, whatever that is, 30,000. And it's just one big, long vector. Okay? And let's suppose that what I'm observing is some noisy version of some underlying image that's blocky, like this thing right here. Okay? It could be due to compression. Maybe I actually, I did something kind of cheap in order to store this, and then I'm sending this to a friend. It could also be like, for example, this was an MRI scan. Okay, but due to nature, the way that the machine works, kind of internally, we don't get to observe things in a noiseless fashion. We observe something kind of which has some nice structure plus some noise. And the goal of our goal as, let's say, a practitioner in image denoising is to denoise this. So to somehow estimate the underlying image from this data. So this is one way to do this. This is called diffuse lasso or total variation denoising. This goes back to the early 90s in applied math. There's a very famous paper that proposes this estimator, and sometimes in applied math called the ROF model, if you're curious. Stands for the three authors. I think it's written in 1992. And basically, it's an optimization problem in which we have one parameter per pixel. So theta I is a parameter that we're going to use to estimate yi, which is the value at pixel I. And we're going to choose theta I to minimize the following criterion. This is just the sum of squares between the observed data and the parameters. Okay, and this part is what gives us some kind of regularity, some kind of piecewise constantness or blockiness. And we're going to penalize the difference between the absolute value of theta I and theta j over all pairs I and j that I'm writing as an edge. And really what all I mean by that is that we're going to say there's an edge between pixel I and pixel j if they're vertically or horizontally adjacent. Okay, so if this is I and this is j, and j is horizontally adjacent, then there's an edge between them. And this is another valid choice, say j prime. So we'll look at all pairs I and j that are horizontally and vertically adjacent, and we'll penalize according to the absolute value of theta I minus theta j with what we call a tuning parameter, lambda, on this penalty term. So these two terms in combination, they provide us with something useful because this tries to get us to fit to the data. This tries to us to fit something that's piecewise constant. And here's an example from this data of a solution to this problem with a particular value of lambda. So I just picked some value of lambda as an example, and I got this as a solution. So you can see it's a pretty good representation of this image. Okay, so this is an example where I spent maybe slightly more time motivating this problem than I would have usually just because it's an intro lecture, but we'll be looking at problems like this throughout the semester that come from machine learning or statistics. So what we care about, of course, is how we got the solution in this class. Okay, so I'm going to tell you about 3 different ways I used to compute the solution. So that's our problem up there. It's actually a convex problem. I maybe should say that because, of course, that's the title of the course. So it's a convex problem that comes with a bunch of things, as we'll learn over the next several lectures, that mean that it's solvable and it's a nice problem. And I used 3 different algorithms that I'm going to show you. I used first what I'm going to call a specialized ADMM algorithm. So ADMM is a class of methods that we'll learn towards the end of the semester. It's very popular nowadays. It stands for the alternating direction method of multipliers. And I used a kind of rather special implementation of this that converged in 20 iterations. So after 20 iterations, each iteration having a computational cost that's linear in n, the number of pixels. So it's very cheap. This was the solution. And that's, in fact, the one that you are seeing. I used a different algorithm called proximal gradient descent, which is, in a sense, a more basic algorithm than ADMM. And you might think is actually, you might think it's better because its iterations may appear to be less complex, which is the case. Iteration by iteration, in this case, it's actually cheaper. But I don't know if you can see from the projector, it gives us something that's actually not really piecewise constant, which we know really shouldn't be the solution, just from what we know about these problems. And even more so, if you were to evaluate, this is a theta. If you evaluate the criterion at such a theta, you can see the criterion value is much larger than what we got from the ADMM algorithm, from this one. So it's actually much farther from optimal. And that took 1,000 iterations to get. Okay, and even if we ran it for, let's say, 1,000 more, we're still going to get these kind of weird curvature, these weird curved regions. It's not giving us something that's piecewise constant. And coordinate descent is the third algorithm that we'll talk about later in the course. It is extremely useful for particular problems. It can set state of the art for a lot of problems. But in this case, it actually performs horribly. Here's 10,000 cycles of coordinate descent, which each iteration is about as expensive as an iteration of proximal gradient. It's still nowhere close to a solution. Okay, so if we look at this theta under the criterion, it's going to be huge, very far from optimal. And just when we learn these algorithms, you'll probably come back to this intro slide if you're curious, and you'll think, how could I apply these two? These last two are applied from the dual. So you can't apply these algorithms to this problem directly. So what I did is I actually derived the dual of this problem, another thing that we'll learn and spend a lot of time on, and I applied these algorithms to the dual problem. There are some questions. Yeah?
It's convex, and I'm saying there should be a single optimum, so how are these answers so different?
So let me break down, and it's a good question. Let me break down that question. The question was, if it's convex, there should be a single optimum. So how are these answers different? So first, convex does not imply that there's a unique solution. I think that's a common, maybe misunderstanding. There still could be a non-unique solution, but they all have to achieve the same criterion value. So that's maybe an important distinction. There's a unique value of the criterion, and they're not separated in some sense, which we'll talk about in the last slide of this lecture. And the reason these are performing so differently is that these things haven't converged. I just stopped them like arbitrarily to show you how they looked after a certain number of iterations. But roughly, all these three algorithms have the same cost per iteration. I mean, the specialized ADMM one is slightly more expensive, but really they're close to the same cost. So, this is a huge difference in terms of where we've gotten after kind of a certain amount of computational cycles. All right. Any other questions?
From machine learning perspective, would it be fair to compare with criterion, or do you want to compare with some other criterion, let's say some head-out?
That's a fine question. In this case, it's kind of hard to talk about held-out data for images, right? We don't really make, if you're talking about image denoising, out-of-sample prediction doesn't really make sense. So this would be a case in which, if we're doing a simulation like this one, it really makes the most sense to talk about maybe either mean squared error on this or maybe the criterion itself. But yeah, it's a fair point. I mean, we could talk about other things like out-of-sample prediction error. Those considerations, though, they're going to kind of all be secondary to us in the sense that we're really interested in optimization. Of course, for problems that are machine learning or statistics, but kind of first and foremost, we're going to try to learn what it means to optimize criterions. Other questions? Okay, all good questions. So let me give you, this is, I guess we never got to the punchline. So what's the conclusion that we should draw from this? I guess we never talked about this. So is the conclusion that you should be drawing from this that the first algorithm, ADMM, is just better than the second two, and that you shouldn't really use the second two in general? So that's not the case, and that's not the conclusion you should be drawing. This is just an example of the fact that different algorithms perform better or worse for different problems. And we're going to be learning details throughout the course. And I'll try to give you kind of like a summary in a big table somewhere towards the middle of the course. It summarizes a lot of the strengths and weaknesses of various algorithms. In this particular problem, this ADMM approach was really fast because we could structure the subproblems in such a way that they were solvable very quickly. So ADMM in general is not like better than proximal gradient or coordinate descent. In this case, the subproblems are very structured. The way we set it up, they're actually very structured. So it took some kind of a special decomposition for that to be the case. Proximal gradient is slow in this case because of poor conditioning. If I go to the dual and you look at the criterion in which proximal gradient is working, if you look at the smooth part of the criterion, there's a very poor condition number. And what we'll see when we talk about kind of gradient methods or first order methods in general is that they actually can suffer quite a bit from poor conditioning. So this just means that actually the criterion itself is very flat around its optimum. Coordinate descent is slow in this case because it's operating on the dual, and in this case the active set, which is the set of coordinates that coordinate descent kind of actively manipulates in each cycle, is very large. And it has to do somehow a lot of work to push those towards optimum. And coordinate descent tends to thrive when we have small active sets. But in this particular case, it actually comes from the fact that we're looking at the dual. The active set's very large. So it's just a bad idea to use coordinate descent. So that was an example of how kind of different algorithms can perform better or worse. Here's another example. Actually, before I do this example, so what I'm going to usually do in this course is try to give you guys a break halfway through, because it's 80 minutes is a long time. And I guess we just went for 50 minutes, so we're a bit over. But let's continue. So there was a very good question that was asked during the break, and I think I just would relay the question because I think it was another good example of what optimization provides us in terms of understanding. So the question was, that was just asked, what happens if I replace this with a squared penalty? It's another good example of something you could figure out how to approach from an optimization lens. If I replace this with a squared penalty, so theta I minus theta j squared, that's actually going to do something very different at the solution to this problem, and it's not going to give us any kind of piecewise constant structure at all. So it's going to be smooth. It's going to be a smooth reconstruction of this image, but it will never give us anything with solid colors like this, where there's a block of solid colors, which I'm calling piecewise constant. Right? So it's one value here, one value here, one value here, etc. And a way to see that is if you want to look back at this after we've talked about the KKT conditions, if you look at the KKT conditions of this problem, you can actually see explicitly that at the solution to this problem, we get exact equality between many thetas. But if we looked at the problem with the square here, it's never going to be the case. Okay, so you can just kind of see from studying those optimality conditions that is the case. You could also maybe guess this is the case by analogy to ridge regression and the lasso. Right? It's similar to what happens in regression with those two types of penalties. Okay, so let me now give you an example of the second thing, which is how an optimization view can provide us with kind of an interesting level of statistical understanding that we didn't have before. So this is an example in sparse linear modeling. Probably a lot of people are familiar with this if you've taken basic ML classes or high dimensional statistics classes. So let's suppose we're given a vector y, which we'll call a response, and a matrix x, which we'll call maybe like a feature matrix. And let's suppose that the feature matrix, so every column of this matrix is a feature, and the number of columns is much bigger than the number of samples, the number of rows. So p is much larger than n. And suppose we know that y is approximately x times beta star. So there's approximately some set of coefficients, right, that if we multiply the columns by these coefficients, approximately reconstruct y. But we don't know what this is. So this isn't, in fact, it could be a modeling assumption, right, that y is close to some linear function of x. And if you had this modeling assumption in mind, you could ask, can we generically solve for these coefficients? Right? Can I just say y is equal to x beta star, let's say, and solve for the beta star in that linear system? Well, the answer is no, because it's underdetermined. So there are many more variables here. So beta star is p-dimensional. So there's kind of p coefficients or p variables. And we only have n observations. So it's badly underdetermined. Let's say in the worst case, if p was very big compared to n, there is no unique solution. We couldn't kind of, in any sensible way, identify beta star from just this working assumption. But if beta star is known to be sparse, which is, again, maybe another assumption, saying that we have many features, but only a few of them are relevant, in a sense, for reconstructing y, then it's a whole different story. All right, so now we're trying to solve a linear system. Maybe I'm still using approximate here. That looks kind of like this. Y is, let's say, 5-dimensional. Here I think I have a 5 by 20 dimensional X matrix. But I'm going to tell you in addition that actually only, let's say, a small number of these columns are relevant for reconstructing y, like in this case 4. Okay, I'm not going to tell you which ones they are, but I'm just going to tell you that there's a small number, say 4 or 5, etc., that are relevant for reconstructing y. Then it's a whole different story in terms of actually we can identify in kind of a variety of ways of looking at it, we can identify these coefficients. So there are many different approaches for estimating beta star in this kind of sparsity assumption. One popular approach is to solve something called a lasso, which is a penalized version of least squares regression. You should be very familiar with this from, maybe previous courses. This is just the least squares loss. This is just the L2 norm between y and x times beta, or the squared L2 norm. If we didn't have this term, then this would just be doing least squares regression. We're trying to find the beta that makes the squared error the smallest. Now we're going to modify this because that is still not generically well defined. We're going to modify this by adding the L1 norm of beta times a tuning parameter to this criterion, which gets something called the lasso. And the L1 norm, just to remind you in case you forgot, is the sum of absolute values of the components. So it's the sum of absolute values of beta I here. And lambda, again, is a tuning parameter. It's kind of like up to the user's discretion in some sense. So there are many algorithms for solving this problem. In fact, this is a quadratic program, or it can be cast as a quadratic program. So you can just use generic QP solvers if you like, that you can find in pretty much any programming language. There are better ways to do it than that. So we'll talk about the lasso. The lasso and SVMs are going to be two things we return to frequently in this course. But if we kind of toss algorithms aside for now, this is a nice example of a problem in which you can draw a lot of statistical insights from what we call the KKT, or it stands for the Karush-Kuhn-Tucker optimality conditions. So it's not something I'm expecting you to understand. We haven't talked about the KKT conditions. I just want to give you a flavor of what you can do with them. So you can write down, it turns out, a set of conditions that are satisfied if and only if you have a solution. So the KKT conditions, they generalize the notion of taking a derivative of a function and setting it equal to 0 as a way of characterizing its minimizer. So they're strictly more general than that. They apply to convex problems in general, with or without constraints. And the criterion doesn't even need to be differentiable. So in this case, this is not differentiable. The L1 norm is actually not differentiable. But we still can get a set of conditions that characterize optimality exactly. And this is what they are. Okay, we have to have x transpose y minus x beta equal to lambda times s, where s has to satisfy the following relationship. It has to basically be the sign of beta when that coefficient is positive or negative, or it can freely vary between minus 1 and 1 when that component of beta is 0. So if we can find beta and s to satisfy these two equations, then beta will be the solution, or actually I'll say a solution to this problem. So it turns out that there was a body of work that all kind of started around the same time that really used these KKT conditions as a jumping point for proving the following fact, which led to a lot of really interesting and important results in high-dimensional statistics. If you have favorable conditions, like for example, the columns of X don't have a lot of correlation between them, so your features are not super correlated, and beta star has a small number of non-zeros, and each one of those non-zeros is kind of large in absolute value. So it's not like it's non-zero but really close to 0. It's actually separated from 0. So those are maybe favorable problem conditions. You can actually show that the lasso solution has exactly the same support as beta star with high probability. So in other words, what the lasso deems to be relevant, so it's going to estimate, I guess I never said this as well, the lasso will generically return for us, and this will be true even more as we make lambda larger, an estimate beta that has many zeros in it. Okay, that's the role of this penalty here. This is going to kind of induce sparsity in the solution. Again, it'll be something that we can see kind of from the KKT conditions once we kind of get familiar with them. And what this result says is that whatever the lasso finds in terms of the sparsity pattern, under favorable conditions, that's going to be exactly the same sparsity pattern that generated y. Let's say the mean of y was x times beta star. The lasso is going to find exactly the relevant features, the ones that have non-zero beta stars. And this is the proof. basically just plug in beta star into the KKT conditions. Okay, not quite beta star, but a shrunken version, because we know that the lasso does some kind of shrinkage. And then show that these are satisfied with high probability. And if these are satisfied, then you have a solution. So that's going to prove that the solution has the same support as beta star. That's basically the whole proof. It's called primal dual witness method. There are some technical things that need to go into making that proof correct, but the idea is basically use these optimality conditions to characterize the support of the lasso. And yeah, it's been a very important result, and a lot of kind of research followed up on that. But we wouldn't have been able to do that without kind of having this this perspective on the lasso. Okay, I wanted to pass on some general wisdom from Jerry Friedman, who Jerry Friedman is a statistician and machine learning researcher who's done a ton of interesting stuff, and he's retired now, but he's responsible for gradient boosting. He wrote the book on classification and decision trees. He's done really just like a ton of very influential work in machine learning and statistics. And he wrote this, so back in 1985, this guy named Peter Huber, who's also very famous, wrote a paper on projection pursuit that got published in the Annals of Statistics. By the way, how many people know what projection pursuit is? Can I see a show of hands? This is what happens when we change the name. This is a one-layer neural net, projection pursuit. So projection pursuit was this old idea in statistics, which is essentially a one-layer neural net with sigmoids. So it got a lot of there's a lot of people interested in this in the 80s in statistics, and then I guess people forgot that was a thing, and now no one's heard of it. But at the time, it was a problem a lot of people cared about, and it was very hard to optimize. It's a non-convex problem. Neural nets are hard to optimize. So statisticians were close to kind of giving up because they weren't sure they knew how to solve this problem. And then Peter Huber wrote this kind of influential review paper of the field, and Jerry Friedman wrote a discussion of this paper. And he had a quote that I really love that supports what I've been claiming, which is that getting immersed in optimization is only going to do you good. And he says, a good idea poorly implemented will not work well and will likely be judged not good. It is likely that the idea of projection pursuit would have been delayed even further if working implementations of the exploratory Friedman and Tukey and regression procedures had not been produced. So this is a bunch of his own work, which actually kind of advanced the numerical state of the art quite a bit at solving projection pursuit problems. As data analytic algorithms become more complex, this problem becomes more acute. The best way to guard against this is to become as literate as possible in algorithms, numerical methods, and other aspects of software implementation. So what he's meaning by numerical methods is what we're calling optimization. I suspect that more important ideas have been discarded because the poor implementation performed badly. So, an interesting question is this less true today? Can you get by with, just using CVX to see whether your ideas work? I claim, it's really still not going to cut it. You really still have to have some working knowledge of optimization for all the reasons I just said. I think it's probably, we're very lucky they have something like CVX or these generic solvers, but still, I think this rings true in large part. Okay, so moving along to the central concept that we're going to be taking in the course, kind of taking note of. So historically, linear programs were the focus on optimization. So in the operations research community, linear programs were in large part the focus on optimization. And if you take optimization courses currently from operations research departments, you'll see an entire course on linear programming. And it was initially thought that the most important distinction between kind of problems that were easy or that were solvable and problems that were really just intractable was linear versus nonlinear. So the moment that you introduce some amount of nonlinearity into the problem, away from linear programs, it became very hard and kind of intractable. But then what ended up happening historically is that some problems that were nonlinear turned out to be much, much harder than other nonlinear problems. And it was not really a very good distinction just to say that nonlinear means hard. Some nonlinear problems were actually quite tractable. And now it's widely recognized that the right distinction is actually not between linear and nonlinear, it's between convex and non-convex. That, if we had to maybe be dichotomous and just think about two different classes of problems, one being tractable, the other being generally kind of very intimidating and intractable, the right distinction is between convex and non-convex. And we can thank actually R.T. Rockefeller for a lot of that. He was very, he was kind of a centerpiece of kind of this convex optimization, convex analysis movement. So 2 supplementary textbooks for the course. So the notes are supposed to be mostly self-contained. I don't think you need necessarily to go read things in these textbooks, although there will be no downside. They're fantastic textbooks. One is Boyd and Vandenberg, which I'm going to, I'll occasionally kind of take graphics from their textbook and put them in lecture notes. I think it's a really wonderful book. It doesn't cover everything. So it doesn't cover, for example, subgradients at all, which is a very important and basic thing that we'll talk about. The other is Rockefeller. So Rockefeller's book is a lot older. It's called Convex Analysis. Just by word of warning, it's much less readable. So it reads essentially like a math textbook that's been compressed down into a tiny amount of space. I think it's just wonderful in terms of how much it covers. So every time somebody says to me, how about this or something in lecture, and I don't know the answer to that, I usually look at Rockefeller first. And usually, after scratching my head for a little while, I'll find the answer. It has a ton of really interesting stuff in it, but I wouldn't look at this book unless you, let's say, come from a math background or are used to reading kind of very heavy, like definition-heavy, theorem-laden textbooks. This one is much more friendly in some sense, but just doesn't have the same amount of material. So, convex sets and functions. That is like our jumping point maybe if we're talking about convexity. I'm just going to remind you what a convex set is, what a convex function is. I'll tell you what a convex optimization problem is. I'll tell you one important property of convex optimization problems. We'll prove it, and then that'll be the end of lecture. So, convex sets. So a set, let's call it C in Rn. This is this n-dimensional Euclidean space. We call it convex if it has the following property. If I take any 2 points from the set, x and y, and I take the line segment that joins those 2 points, so that's tx plus 1 minus ty, as I let t vary between 0 and 1, that whole thing has to be contained in the set C. Okay, so this polyhedron here that I drew, it is convex. It has the property that if you take any point x, any point y, and I looked at tx, this is maybe, if I look at the midpoint, that's going to be half x plus half y. Maybe let's say 0 is somewhere in the set. Then this is going to be in the set, but the same is going to be true for every other value of t. For a different value of t. Okay? This is a non-convex set. For some values of t, this line segment, right, that generates this line segment, for some values of t, it's going to leave this set. So convex sets we'll talk about in great detail next time, probably for half or more of the next lecture. And in many ways, convex sets are a more fundamental object than convex functions. And what I mean by that is that everything you know about convex functions can be derived from a property of convex sets. So convex functions are easy to work with. We're gonna have basically, I think, we'll pay much more attention to convex functions as the course goes on than we do to convex sets. But really, all of the key properties all derive from what we know about convex sets. So convex function, we're going to be thinking about functions that map Rn to R. So they go from n-dimensional Euclidean space, and they just return for us a single real number. We could say that a function is convex if its domain is convex. Okay, so what is the domain of a function? So it's the set of all x such that f of x is, let's say, defined and finite. Sometimes we might drop this. Sometimes we might allow infinite values, but then in that case it'll become clear. Right? So, for example, if I look at the function log x, if I take f of x to be log x, its domain is, what do you guys think? We sometimes write it like this, r plus plus. It's just the set of all x. Yeah. It's just a set of all x that are positive. And I'll often write that as r plus plus. The two pluses are for the strict inequality here. I'll write 1 plus for bigger or equal to 0. Okay, in any case, this function has some domain. It may not be defined on all of Rn. For it to be convex, we require this to be a convex set. So that's kind of one precursor. This is the key property. If I take any 2 points on the graph of the function, and I look at the line segment joining those 2 points, the function value must lie below this line at every argument between x and y. Okay, that's what this is saying. F of tx plus 1 minus ty must be less than or equal to tfx plus 1 minus tfy. That's just the mathematical version of what I explained. Right, this is the line segment joining f of x and f of y. As I let t vary between 0 and 1, that's this line. And this is the function value at all those points in between x and y. Okay, so hopefully that's something you guys have seen before, or if not, it'll become very natural to you to think about some convex functions. So I haven't told you convex optimization problems are so great yet. We'll get to that in just the next slide. But let me tell you maybe formally what it is. So here's a generic form for an optimization problem. Okay, I'm just writing it in this form. It could take other forms, but this is maybe in some way the simplest way to write it. I'm going to minimize over all points x in some set D, the criterion f of x, subject to these constraints. Gi of x is less than or equal to 0 for a bunch of different i's, and hj of x is equal to 0 for a bunch of different j's. So I should also say this is an optimization problem. There's nothing convex about this if I just write this down. It's just an optimization problem. I haven't told you what makes it convex yet. And D, what's that D? It's the common domain of all the functions. Okay, so it's just the set of all x for which all the functions in the optimization problem are well defined. So we call this the criterion. We call these inequality constraint functions and these equality constraint functions, gi and hj respectively. So that's an optimization problem. A convex optimization problem is one of this form, where f is convex, each of those gi's is convex, and each of those hj's is affine. Okay, which means that it can be written as this linear function of x, aj transpose x, for some vector aj, plus a constant bj. That's what a convex optimization problem is. Okay. So why do we like convex optimization problems? It's really because of the following property. And I think we'll have time just to prove this, and then that'll be pretty much the end of the lecture. So for a convex optimization problem, we have this really important property, which is that any local minimum is automatically globally minimal. So we don't have strictly separated local minima. And what I mean by that formally is as follows. If we have a point x that's feasible means it satisfies all these constraints, gi of x less than or equal to 0, hj of x equal to 0, and it has to be in the set D. Okay, from now on, actually, I think pretty soon I'm going to drop this D from the picture. I'm just going to assume that all the points we're talking about are in all the domains of our functions. Okay, so we won't really make this explicit anymore. Otherwise, we can't even talk about what gi of x looks like for some functions. So it's feasible if it satisfies all the constraints and it's in the common domain. And if it's both feasible and it satisfies this property in some small neighborhood, f of x is less than or equal to f of y for all feasible y that are within a ball of radius rho around x. So this just means, if I'm at x and I look at a ball of radius rho, an L2 ball of radius rho, so all the points in this ball have the property that the L2 distance between x and y is less than or equal to rho. That's this property here. I look at that ball, and I look at all the points in this ball that are feasible from an optimization problem, which means that they satisfy these constraints and they're in that domain. Then x wins in terms of the criterion value. So this is what it means to be locally optimal. This is the definition of locally optimal. Okay, where maybe the radius here is rho for that local neighborhood. The key property of a convex optimization problem is that locally optimal points of this form are globally optimal. So anything that satisfies that property automatically satisfies f of x less than or equal to f of y for all feasible y, which again means that it's globally optimal. And we're done in some sense. So it's very useful. It's going to save us a lot of trouble. And I just gave you kind of two different surfaces, convex and non-convex, to show you that there could be locally optimal points, right? Imagine if we extended this surface over here. There could be a locally optimal point here. I could look in some ball of radius rho. It could look like it's better than everything in the ball, but actually maybe I was forced to go over here to get something that's globally optimal. That can't happen in convex optimization problems. That's what the statement is saying. Okay, so let's prove this. Okay, so we're going to do it by contradiction. So we're going to say, suppose there's some feasible point, z, such that f of z is strictly smaller than f of x. Right, so we have some x that satisfies this local optimality property. If it's not globally optimal, there's some other point z that's feasible that has a strictly smaller criterion value. So picture-wise, z must be out here. Right? We know that z can't be in this ball because x is locally optimal. It has a better criterion value, or at least the same criterion value as everything in that ball. So if there's something else better than that, it must be out here. So what we're going to do, okay, is that we're going to actually look at the line segment joining z and x, and we're going to actually look at a point on that line segment that's in the ball. And we're going to prove using convexity that if f of z is smaller than f of x, then that also must be true of this point. And that's going to be our contradiction because x is optimal within this ball. Okay, so let's consider tx plus 1 minus t z. Okay, for some t between 0 and 1 that we're not going to specify yet. Let's call this y. So first of all, we've got to get some stuff out of the way. Y is actually still going to be in D. That's one fact. So this is fact 1. Why? It's because D is actually an intersection of convex sets. Okay, and from what we're going to learn next time, intersections of convex sets are still convex. So I took one point z that's in D, another point x that's in D, and this is a point on the line segment in between the two of them, so it must also be in D. All right, just using this property of convex sets here. That's it. Okay, the other fact that we're going to use is that all the gi of x's are less than or equal to 0. That's true because, sorry, I should say y at the point y. That's true because if I take gi of tx plus 1 minus tz, because g is convex, this gi is convex, that's less than or equal to t times gi of x plus 1 minus tg of z. Definition of a convex function. And each of these is less than or equal to 0, right? Because x is feasible and z is feasible. So if I take t times something less than or equal to 0 plus 1 minus t times something less than or equal to 0, I still get something less than or equal to 0. So y satisfies all the inequality constraints. It also satisfies all the equality constraints. I'll let you check that one. It's even easier. So, in other words, we've proved y is feasible. Okay, so at least everything on this line segment is actually feasible for optimization problem. Okay, and now we're going to actually let's look at the norm of y minus x. Okay, this is going to be maybe yeah, this is fine. This is going to be t x plus 1 minus t y. Thank you. This is supposed to be z. Minus x. Okay, and I can just pull out the common factor of 1 minus t, and this is just 1 minus t times the norm of z minus x. And therefore, I can choose t close to 1 to make y minus x less than or equal to rho. Okay, because this is just something fixed. This is some fixed distance like r. I can make this arbitrarily small by taking t close to 1, but not equal to 1. So I can just take this very close to 1 and make this less than rho. Right? There's nothing stopping me from doing that. So I've just argued that actually I can get y in this ball if I take t close enough to 1. And the last thing that we need to do is actually show that for whatever value of t that is, it's not going to be equal to 1, but it's close to 1. We actually have a better criterion value at y than we do at x. Well, that's going to be our contradiction, which means that such a z cannot exist. Right? Such a z could not exist in the first place. And so far we've used convexity of the domains, we've used convexity of the g's, convexity of the h's. The only thing that's left to use is convexity of f. Right? That's really all we know so far. So let's do that. If I look at f of y, right, that's going to be f of tx plus 1 minus t z. And that's less than or equal to, by convexity, tfx plus 1 minus t f of z. And now you should convince yourself that if f of z, actually I can just say f of x is strictly, f of z is strictly smaller than f of x, right? So this is strictly smaller than t times f of x plus 1 minus t times f of x. Just using the fact that this is strictly smaller than f of x by assumption, and that's just exactly equal to f of x. Okay, so that's our contradiction. Okay, so that property does not exist for non-convex optimization problems. You can have very complicated landscapes of optimization services, but it does exist for convex problems. And the second thing that you're going to see as we go on through the course is that not all convex problems look like this. It's actually still a very expressive class. So it still is a very big class of problems. We can model all sorts of interesting kind of phenomena with them. So this kind of flexibility or expressibility paired with the fact that we don't have this big issue, we can always kind of think about things as being globally optimal, makes them kind of a very interesting and tractable class to study. So that concludes the first lecture. I will see you guys on Wednesday. Oh, last thing, sorry. Don't forget to take your quiz. I am 1 minute over, so I'm just going to do the first question on the quiz for you. Sorry that I forgot. Here you go. Here's an example. If f is a convex function, then a valid constraint in a convex optimization problem is f of x equal to 0. So actually, we saw that that's not true in general, because we have to have affine functions for equality constraints. So even if you clicked true, you'd see it says, sorry, only linear equality constraints are allowed. And then you click false, and you get half a point. So there's 7 more questions. Now you know the answer to the first one. And it should not be very stressful. So make sure to do your quiz.